How's that? There we go. That looks better. Sorry about that. Looks like we had some audio disconnection there, but hopefully you can hear me now. So welcome to the Neo4j stream. This is the GraphQL and Grand Stack edition. We have been working on building a travel guide using Neo4j, Gatsby, and GraphQL. And we're going to continue working on that project today, picking up from where we left off last time. But before we get into that, I want to mention a couple of things that may be of interest. So the first thing I want to talk about is the upcoming Nodes conference. That is the Neo4j Online Developer Expo and Summit. This is an online conference all about graphs and Neo4j. The first one ever was last year in October. So this is the second iteration of this conference for 2020. It's a free conference. It is October 20th. The agenda is out, so you can check that out. I'll drop a link to this in the chat. So be sure to register if you want to tune in for all kinds of exciting announcements from the Neo4j community, developer deep dives on lots of interesting topics, a few including GraphQL and Grand Stack, but also things like graph data science, graph algorithms, deep dive into how things work in Neo4j tooling, how to use Neo4j with different frameworks, all kinds of stuff there. So that's the first thing I wanted to mention. And the second thing I want to mention is, let me find the short link to this. Here we go. Here's the short link for this. So I think, as a few of you know, I've been working on a book for a while now called Full Stack GraphQL. This is published by Manning, and it's an early release from Manning. There's, I think, 5 or 6 chapters out now, so almost done there. But there is a excerpt of 3 chapters that's available for free now if you go to this site, and you can download the first 3 chapters that talk a lot about how to use GraphQL with Neo4j. It's kind of the focus on this excerpt is kind of how do we build the backend in the context of full stack GraphQL. So if that's of interest, you can download that for free. I want to do a sort of a book club on the live stream. So I think we will start that on the stream maybe once we finish up with the Gatsby project. We'll switch over to sort of a book club where we work through the exercises in this excerpt, so the first 3 chapters that are in there. So if that sounds interesting, download the book and stay tuned on the stream for when we can go through that as a book club. Okay, cool. So let's get into it then. So again, as always, if you have any questions as we go through this, feel free to drop it in the chat. Doesn't necessarily have to be what we're talking about. You can ask about anything, and we'll dig into it. So picking up from where we left off last time, so I have the README open here. Let's take a look on GitHub. GitHub, Johnny Montana, what do we call this? Central Perk? Yeah, there it is. So here's the link. So this is what we've been building. So in the first session, we talked a little bit about the data set that we're using, which is this OpenStreetMap import of data of Central Park in New York City that's available as a Neo4j sandbox. And if you don't have that, here's the link to download that. Inbox, there we go. This one is still kind of a hidden sandbox. So you'll want to use this link that has the use case equals OpenStreetMap query param in there so that it will unlock the this OpenStreetMap sandbox, kind of a direct link to that. There's lots of other data sets, but this is the one that we're using with Sandbox. So anyway, so the first session we looked at that. We looked at how to create a GraphQL API using this data in Neo4j Sandbox using Neo4j GraphQL JS. So that is here. So this is a Node.js GraphQL server that we built just by defining our type definitions and using the power of Neo4j GraphQL JS to spin that up. Then at the same time, we created a Gatsby project using the Gatsby blog starter. Then the next session, we looked at how do we pull data into Gatsby from the Neo4j GraphQL API. That was part 2, to populate our pages. So basically what we have are points of interest from OpenStreetMap. And in our Gatsby site, we want to build sort of a detail page for each point of interest that has pictures, information, that kind of thing. So in the last session last week, we looked at how do we create custom resolvers in our Neo4j GraphQL API to, one, call out to Mapillary. So the Mapillary API is kind of like a crowdsourced Google Street View. It allows us to find images that are showing certain areas. So we pull in those Mapillary photos, and then we saw a different way to add custom logic to our GraphQL API. In this case, searching Wikipedia using APOC load JSON within Cypher. So that was pretty neat because that allowed us to add Wikipedia data to our Gatsby project. So let's start this up. So I'm going to go to the Neo4j GraphQL directory and start our GraphQL API. So that's going to start this project on localhost 3003. So this allows us to do things like querying for points of interest. Let's grab the first, the first 10 here. Make sure that works. Yep, so that's pulling data down from my Sandbox instance, which I have running here. So I'm connecting this GraphQL API that I'm running locally to this Neo4j Sandbox instance running in the cloud somewhere with my OpenStreetMap data. And now let's open a new terminal tab and cd into Gatsby site, and we'll do a Gatsby develop. And what this is going to do, so this is going to pull in this Neo4j GraphQL API, pull that into the Gatsby GraphQL API. Looks like we had an error there in our GraphQL query. We'll have to figure that out in a second. Okay, let's see what mistake we made here. Maybe let's do a Gatsby clean to clean the cache. I don't think I've changed anything since we left off last time, but yeah, looks like we do. So it doesn't like photos. Do we not have photos? We added photos. First one. Ah, okay, so a few things going on there. So one thing, if you notice, when I didn't include latitude and longitude in my selection set, I get an error that says, cannot read property longitude of undefined. But when I add location, latitude, and longitude, now I'm getting a different error. This is, I think, a mapillary API key that we'll resolve in a second. Let me stop the Gatsby build. The reason for that, if we look at the photos resolver here, is it is assuming that we have a location.longitude and location.latitude fields that have been resolved. So those are kind of a dependency to be able to fetch photos from the mapillary API. So what we really should do, there's a way that you can declare fragments to be a dependency. So it's sort of a GraphQL transform to add fragments to a request. We should take a look at that. What I did that we didn't run into this before is because in the query that we're using in Gatsby, so let's jump over there. The query that we're using in Gatsby, if we look at the source template blog post and look at this query. So in this query, we're pulling in latitude and longitude already. So there's only one query in Gatsby where we're pulling in photos, so that's being included in the blog template component. So we should look at how to fix that properly, but as long as we include latitude and longitude, we don't get that error in the photos resolver. But the error we have now, when we call out to the mapillary API, so back in our Neo4j GraphQL project, when we call out to the mapillary API, we need a mapillary key from, we're reading from an environment variable, and it looks like we maybe forgot to define that. So I have a .env file. Oh yeah, so somehow that got removed. So this is, I think, mapillary key equals, let me sign in to mapillary here. I'll do that down here so we don't have to look at my keys for all of my mapillary projects. Not really that big a deal. Let's see, developers. We want the client ID. Yeah, copy that. No, we'll get to see it anyway. That's fine. Okay, and then I think we need to restart our Neo4j GraphQL API. And now, if we add photos, we should call out to the mapillary API, find some photos. There we go. Now we've got some photos. Okay, cool. So back to Gatsby. Let's do a Gatsby develop. And that'll take a sec to build. If you remember, when we added the call to the mapillary API, that slowed down our builds because we have to make a request for each point of interest as we're building all of these pages. So while we're waiting for that to build, a question from the chat, does Neo4j have a Docker image? Yes, Neo4j does have a Docker image. If we look at neo4j.com developer, and the developer guides, and if we search for Docker, there's a developer guide on using Neo4j with Docker. So neo4j.com/developer/Docker. So there is an official image. There's some guides here that talk about how to use Docker with different kinds of configurations. You can even install plugins and so on. So lots of options there. There's also, so if we take a look at the Neo4j Labs page, so Neo4j Labs is a team that builds sort of more experimental integrations and extensions for Neo4j. It's actually the team that I work on at Neo4j. So these labs projects, they're not yet, I should say, officially supported pieces of the product. They're more experimental with the idea that once they're sort of validated and incubated, then they move on to become official parts of the product. The thing I want to mention there, because you asked about Docker, is Neo4j Helm. So if you're interested in using Neo4j in Kubernetes, so basically orchestrating Docker containers, there is a Helm chart for using Neo4j, which allows you to deploy a cluster, a Neo4j cluster in Kubernetes. So anyway, since you asked about Docker, that might be of interest. Okay, looks like our Gatsby build finished with a few warnings because I left a few things out. So we can clean those up later, that's fine. So let's go to localhost 8000. And so if you remember, what we did is we built this index page that just lists every point of interest from the database. And then we have a detail page where in the URL, this slug is the OpenStreetMap node ID for that point of interest. So anyway, so here's our picture of the point of interest, in this case, this reservoir from Mapillary, the details we have from OpenStreetMap, and then pulling in data from Wikipedia for our travel guide. Okay, cool. So that's where we left off last time. And what I want to do next is start to add some maps to our project. So I think we want to have a big map on this index page that basically has, here's a map of Central Park and markers for all of these points of interest so we can see where they are, and then sort of click on a marker and it links to one of these detail pages. Right? So that's the goal for the index page. And then for these detail pages, what I'd like to do is have a map that shows where this specific point of interest is, but then allows you to find a route to your next point of interest. So show you the path for the next point of interest that you want to go to, depending on what you select. So that's what I want to start working on, is this map functionality. But first we need to take a look at routing. So how can we go from this Three Dancing Maidens statue? Maybe I want to go to next, what would be a fun one? Maybe Crime Busters Rock? Sure. So I want to be able to see a map and show me a path on that map of the best way to get there. If you've ever been to Central Park, you'll know there's a lot of little bike paths and sidewalks and paths through the woods and streets. So it's pretty easy to get lost there. So we definitely want to have some routing to tell us where to go. So that's, I think, what we'll focus on today is let's update our GraphQL API to have better routing between 2 points, any given 2 points of interest. And we did this a little bit, if you remember, let's say we want to go, let's return the node OSMID in this GraphQL query as well. We can take the photos out. We don't need the photos. Make this a bit bigger. So let's say we want to go from the Jacqueline Kennedy Onassis Reservoir to this Robert Burns statue. So I'm just going to copy that node OpenStreetMap ID. And if you remember, we added this route to POI this route to POI field that then, so it takes a POI and then returns a list of these latitude, longitude objects. And it's complaining about, oh, expected an integer, right? But we actually want this not to be an integer. We want this to be of type non-nullable ID. If you look at that, is the type we're using for the node OSMID. Not sure why we left that as an int. Anyway, okay, now if we run this, I must have, oh right, just the first one. So we were getting an error there because I was trying to calculate routes for the first 10 points of interest, which included the Jacqueline Kennedy Onassis Reservoir. So we got an error saying I can't route to myself. But if we search for just, so find the first point of interest, which is the Jacqueline Kennedy Onassis Reservoir, and then route to this other point of interest by this ID, which is the Robert Burns statue. It gives me this latitude and longitude series of steps to take. So what we want to do in the application is allow someone to select some other point of interest, and then on the map we want to use these latitude and longitude pairs to draw a path so they know where to go. But first, let's look at how this route to POI is being calculated. So that is this field. Let's make this a bit bigger. There we go. So that is this field, route to POI on the point of interest type. And we can see that it takes as an argument POI, which is the ID of the other point of interest I want to route to. And then it's going to return a list of step objects, where step objects is just, for now anyway, latitude and longitude pairs. Okay, so then we add a cipher schema directive. And that cipher schema directive allows us to attach a cipher statement to our GraphQL fields. This is saying anytime you request route to POI, I'm going to execute this cipher statement to resolve the data for this field. And if we look at what we're doing, we are matching on a point of interest node, so finding the point of interest we want to route to. So anytime we use a cipher directive and have an argument on that GraphQL field, any of those arguments are passed into the annotated cipher statement as parameters, as cipher parameters. So here the argument is POI, it gets passed in as a cipher parameter. $POI is the syntax for using cipher parameters. Okay, and then once we match on that, well then we use the shortest path algorithm to find a path following these route relationships to the other point of interest up to 200 hops deep. And once we find that, then we just grab all of the nodes from that path and return this latitude and longitude object, which matches this step object. So step is not an actual type in the database. We don't have any step nodes. Instead, that's something that we're just projecting out from this cipher query. So we can do that with these cipher directive fields, as long as we don't go too crazy in the kind of nested selection that we want to have. We can return objects that map to types in our GraphQL schema. Okay, so it would seem like, hey, we've got this shortest path function in Cipher. We've got a route. It's giving us latitude and longitude. That should be good enough, right? Like, why don't we just put a map on this and call it a day? And what I want to show is that this shortest path function in Cipher is giving us the shortest unweighted path. So in the graph, it's looking at the path from the Jacqueline Kennedy Onassis Reservoir to the Robert Burns statue, following the route relationships. It's finding the shortest path measured by the number of relationships to follow. But really what we're interested in is the shortest distance between those two nodes. And each one of these route relationships has a distance property. So we know each step, basically the cost, the weight of that relationship. So to go from, say, this point to this point, I don't know, maybe that's 50 meters. To go from this one to this one, that might be 5 meters, and so on. And the true cost is the sum of that path. So unfortunately, the shortest path function here that we're using is not giving us the shortest weighted path. It's just looking at the number of relationships in the route. So what we want to do is figure out how we get the shortest weighted path. But to do that, and to sort of prove to ourselves that we're not getting the shortest path by distance, what I want to do is take a look at some tooling for Neo4j Desktop that allows us to visualize this spatial data, including these routes that we're looking at. So I'm going to switch over to Neo4j Desktop. From the chat, question to zoom in. Yeah, hopefully that was big enough here. I think if I go any bigger, I can't really fit much on the screen. So hopefully that was good enough zoom level. And another question: what about previous videos of the series? Yeah, so if you look at the GitHub page for this project, all of the live streams are recorded on YouTube, and they're linked here. And I won't click on one of these because it'll start playing, and we'll be watching a stream from within a stream. But you can find the recordings there, and there's a YouTube playlist that has all of the recordings for this project, for the previous one we did, which was the real estate app, and then there's another playlist for all of the GraphQL and GrandStack videos that we've been doing. You can also, if you look through the commit history, there should be, yeah, so there's like one commit for each one of the streams that we do. So you can follow along that way too. Cool. Okay, so what I want to do is figure out how I can visualize some of this spatial data. So I'm going to switch over to Neo4j Desktop. So Neo4j Desktop has these things called graph apps. So these graph apps are applications that you can add into Neo4j Desktop that kind of enhance the functionality of what you can do within desktop. If you haven't used desktop before, you can think of desktop as kind of like mission control for Neo4j. So it allows you to have multiple projects, and then within each project, you can have multiple databases. So I'm going to create a new project. Let's call this Central Perk. And I can create multiple databases for each one of these projects. I can download a database locally. I can choose a bunch of different versions, but it also allows me to connect to remote databases. So if I'm hosting a database in the cloud somewhere, if I'm using the Neo4j Aura cloud service, I can connect these databases in desktop to remote Neo4j instances, and then I can use all of the functionality within Neo4j Desktop, including these graph apps with those remote databases. So that's exactly what I want to do, is connect this database to my remote sandbox database. So let's call this my OSM sandbox, and if I jump to sandbox, I can get my connection credentials. So there's the Bolt URL, and we'll do username password authentication. So the user is always Neo4j on these sandbox instances, and then here's my random password. So this will now connect Neo4j Desktop to my remote sandbox instance, and I can open up Neo4j browser to prove this. So let's do a, this bigger, let's do a call db.schema visualization. And yep, here's my data model. Got all kinds of OpenStreetMap data in here, including my routing graph, which is what I'm most interested right now. Cool, so that looks good. You'll see this, the Summer of Node browser guide when you first connect to this. That's because you originally used this data set as one of the Summer of Nodes challenges. So if you've seen that before, that's where that comes from. Okay, cool. So that was Neo4j browser. But if I click on this down arrow, I can see all these other graph apps that I can use to work with my sandbox instance. You may not see as many of these. You may need to install some of these if you're not seeing them, but you can open the Graph Apps Gallery to see what is available. So the Graph Apps Gallery showing all of these graph apps that you can install. Most of these you can install with just one click here into Neo4j Desktop. So there's a ton of things here from the ETL tool for importing data from relational databases, Halen for monitoring your Neo4j cluster, the Graph Data Science Playground, which is kind of a low-code environment for working with graph data science, GraphQL Architect, which we've taken a look at before in this stream. This is for building and querying GraphQL APIs with Neo4j. But the one we're interested in today is NeoMap, which is this awesome graph app that allows us to visualize spatial data that Estelle wrote and maintains. So click install for this. I'm not going to click it because I've already installed it. But if you click that, it will install NeoMap, and then you will have that available to connect to your sandbox instance. Cool. So the idea with NeoMap is to basically allow us to create layers to visualize spatial data from Neo4j. So I'm going to create a new layer. And the first thing I want to do is visualize all of the points of interest. So let's call this layer POIs. And we want to choose the type of the layer. So if we're going to give individual latitude and longitude values stored as individual like floating point properties, or if we're using the point database type, which we are, so we'll select that. We can also define layers with cipher queries, which we'll do in a second when we start looking at routing. But for now, we want just points. So what labels? We want to look at all of the point of interest labels. We're storing the point location data in the location property. And then for the tooltip, we'll show the name of the point of interest. For the maximum number of nodes, well, I think we have like 100 and some points of interest, so we'll set that at 200 and it'll show us everything. And we want markers. Okay, so we'll click Update Map, zoom in on Central Park, and after all those markers are added, we can see our points of interest on the map. Cool, so here's Central Park. I can zoom out a bit. So here's New York City, here's Manhattan, and Central Park is this giant park in the middle of Manhattan. So all of our points of interest are within Central Park, since that's where we trimmed the OpenStreetMap data import that we're using. Cool, and I can click on some of these and see the name of the point of interest. There's a big cluster here. What is this? Oh, this is a bunch of tennis courts. If you remember in our Gatsby blog, we had a whole bunch of points of interest called pitch. So I guess each one of these courts has its own point of interest called pitch. Here's the Jacqueline Kennedy Onassis Reservoir. Cool, okay, so we have our points of interest marked on the map, so we can sort of see where these things are that we're talking about, so that's cool. And what I wanted to prove to you is that the cipher shortest path function is not giving us the optimal path, that instead it is giving us the shortest path measured by number of relationships, but not by distance of the path necessarily. So let's take a look at that and see how we can visualize the path for that route. So here's the cipher query we were using. For the shortest path function. So let's jump into Sandbox. We'll jump into Neo4j browser just to get our query right. Okay, so first let's match on two things here. So point of interest, let's look these up by name. That should be a bit easier. So we're going to say match node A, where the name is something, and node B, or the name is something else. And then find the shortest path between A and B instead of this and other. And then grab all of the nodes in the path and return latitude and longitude. Now, we're going to use this query in NeoMap, and it expects us to return a latitude value. So we're going to alias this to latitude and in.location.longitude as longitude. So with GraphQL, we want to return an object with those values because we're mapping that to that step type in our GraphQL schema that we looked at earlier. So we want to match the shape of that object. But with NeoMap, since we're going to visualize these in NeoMap, we want a latitude and longitude value in the return. Okay, if we run this, we're going to get nothing back because we need to first match on these 2 points of interest that we want to go from and to. So we were looking at going from the Jacqueline Kennedy Onassis reservoir to, I don't have the name here. I have the ID. I can find that. Was it, I think, the Robert Burns statue? Let's look that up. So I'm just switching to a different Neo4j browser instance just to look up the name of that point of interest. Oh, I guess we could do it in GraphQL, couldn't we? Let's just do that. Point of interest, node OSM ID is this. What is the name? Robert Burns. Not Robert Burns statue, just Robert Burns. Okay. And if we run that, cool. That should be the same as this query. Cool. So this is now the same route that we were getting in our GraphQL API, just in Neo4j browser. And what I'm going to do is copy this query and switch to NeoMap. And now what I want to do to visualize this path, I'm going to add a new layer. And we'll call this shortest path. And the layer type is now going to be advanced cipher query. This is the cipher query that I want to use to define the layer. And this is going to be a polyline because I want to see the path drawn. Let's pick a different color, something that stands out so we can see this. Kind of yellow and green and stuff. Should we just do a dark red? Yeah, how about that? Okay, let's see if that works. Okay, cool. So here's our path from the Jacqueline Kennedy Onassis Reservoir. Looks like we get on this this running track, and then you can see this isn't quite perfect because we're jumping across the water here, but you can see that it does continue along the edge here. Okay, and then we're sort of making our way on East Drive and some trails to get to this one, which should be our Robert Burns statue. Okay, that actually doesn't look too bad. So that might actually end up being an okay path, but let's see how we can compute shortest weighted path and see if these paths end up being different. So is the water deep? I don't know. That's a good question. Can you swim in it? I don't know. I know they have those like rowboats that you can rent. I don't know. I mean, it's a reservoir. It looks pretty big, so I imagine the water's pretty deep. Probably not something you want to try to walk across. Okay, so that's how to visualize the cipher shortest path. How do we do shortest weighted path? Well, let's go to the docs. So we're going to use the Graph Data Science library, which is a plugin for Neo4j. You can install it in Sandbox with just one click. You can download it and install in a Neo4j instance. It comes by default in Sandbox as well, so it's might as well consider it part of Neo4j. And there's a number of algorithms that are available in this graph data science library. If we look at the docs here, make this a bit bigger. Sort of the classes of algorithms are centrality, community detection, similarity, pathfinding, link prediction, and node embeddings. And then there's a Preagle API for you to build your own algorithms with. So centrality, these are going to be things like PageRank and betweenness centrality that allow us to find the sort of like the most important nodes in a network, find nodes with a high influence, that sort of thing. For the community detection algorithms, these are going to be things like Louvain, label propagation, those sorts of algorithms that are going to be finding communities and clusters in the graph. These similarity algorithms, most of these are actually, I guess, what you would call set comparison operations, where you're comparing maybe two vectors of ratings for movies or music or something like that. And you want to come up with a measure of how similar two users' interests are. So these are very useful often for recommendations. So if I want to recommend a book or music or restaurant, I want to find users that have a similar taste as myself. And one way to do that is to calculate similarity between two users using their ratings on previous products. But anyway, the algorithms that we're interested in today are these pathfinding algorithms. And specifically, we're going to start with shortest path. So shortest path, this is Dijkstra's algorithm, essentially. Here's the, let's see, do we have a good diagram of Dijkstra's? No, let's jump over to Wikipedia. So Dijkstra's algorithm. So if we take a step back and look at our data, let's look at I guess just the first one. So this is, which one is this? This is our Jacqueline Kennedy Onassis Reservoir again. And if we expand out a few hops, so here's some sort of metadata associated with it, but these are the nodes we're interested in. So what we're doing to find these routes is we're following the route relationships, and these are connecting nodes with the label OSM node. So these are OpenStreetMap observations for different, they're called ways, but you can think of them as like a path, essentially. And so what we're doing is following these route relationships. Some of these OSM nodes are going to be intersections or points of interest themselves. So you can see we have multiple labels here. So this Jacqueline Kennedy Onassis node, Onassis Reservoir node, is an OSM node, it's an intersection, and it's a point of interest. So what we want to do is follow these route relationships from OSM node to OSM node until we get to our other point of interest. that we're trying to reach. And to do that, we need to use a graph search algorithm to do that. The shortest path algorithm in Cypher that we were using before, that implements what's called a binary breadth first traversal. So it's basically starting from the starting point and the ending point. So in this case, both of our points of interest, and doing a breadth first search going out from each one of those nodes. So because it's coming out from both of those points at once, it's typically pretty fast, and it's always going to find the shortest path in a breadth first manner, but not looking at the weight of the path. So if we look at these route relationships, we can see that there's a distance property. So this one is 9.48 so meters. From this node to this other node is 39 meters. So they're not evenly spaced. So we're not necessarily going to get the shortest path using that breadth first traversal that the shortest path function gives us. So for that, we want Dijkstra's algorithm. And Dijkstra, the way this algorithm works, you can think of as a breadth first search, where we're sort of looking at each of the neighbors in each iteration, and then the next iteration of the algorithm looking at all of the neighbors we've explored so far, and continuing on that way until we have reached the destination. But the difference with Dijkstra is that along the way, we calculate the sum of the path that we have found so far, and we prioritize the routes with the lowest cost. I think there's, yeah, here we go. So here's a video sort of how this works, where the red nodes are all of the nodes that we've explored, trying to get to here, and we're prioritizing the nodes with the lowest cost. Okay, so that's the algorithm. How do we actually use it? Well, here's the documentation in the Graph Data Science library. We call it the shortest path algorithm. It's really Dijkstra. So Graph Data Science exposes these procedures namespaced with GDS. So to use the Dijkstra algorithm, we'll say call. So call is the syntax for calling a procedure in Neo4j. Call gds.alpha. So this alpha, this is indicating the tier of the algorithm. So in the data science library, there are, like I showed, a number of categories of algorithms. So there's different implementations in these different categories of different algorithms. And some of these algorithms, the implementation has been optimized, all the edge cases have been figured out, it's really fast, we can use it on massive data sets, and we have a lot of certainty that the algorithm is going to be performant, or this implementation of the algorithm is going to be performant. Those are in what's called the product tier. So those are the officially supported algorithms. Others are namespaced in alpha, which means it works, it's an implementation of the algorithm, but it may not have been optimized for the best performance or scale at this point. So sort of a use at your own risk kind of warning. So that's where the alpha namespace comes in. And then the name of the algorithm, in this case, shortest path. And then we can either stream or write. So in this case, we don't want to write back to the database the result of the algorithm. We just want to stream the results out. Here's the different options. And let's find an example here. So here's an example. We're creating some road data. So we match on the two locations that we're interested in. We call GDS alpha shortest path dot stream. And then we have to create a node projection and a relationship projection. So what is that? Well, what graph data science is doing behind the scenes is constructing a projection of the graph that's stored in the database. Oftentimes we want to run our algorithms not necessarily on everything that's stored in the database, maybe just some subgraph, maybe some projection of the graph. Maybe we want to run our algorithm on sort of an inferred graph. That's often the case in things like social network data. So we can define that projection using a cipher query, like we're doing down here, or we can define that projection using some configuration to specify the nodes and relationships we want to follow, which is what we're doing here. Okay, so let's modify. Where did it go? Not there. Here. Let's modify this query to now find the shortest weighted path using Dijkstra's algorithm. So what we're going to do, we are matching on the first 2 points of interest, so A and B. So that looks good. Let's get rid of this. So we'll say call gds.alpha dot shortest path dot stream, and now we pass in some configuration. So for the node projection, we want to look at OSM nodes. So all the nodes that we're following, both our point of interest and the nodes that represent the spaces on the path that we're following, those all have the label OSM node. And then we need relationship projection. And here we're specifying all of the relationships that we want to bring into this projected graph. In this case, it's pretty easy. We just want the route relationship. So that becomes the key in this configuration object we're passing to relationship projection. And we can specify the type. So we want the relationship route type, and then any properties we want to bring through. And we're just interested in distance here. That's the only relationship property that we're interested in. And then the orientation, do we want incoming, outgoing? In this case, this is undirected because, I don't know, we're not concerning ourselves with sort of one-way streets here. We're saying, assuming you can go either way on any of these paths. Okay, so that's the relationship projection. And we need to specify the start node. So that's going to be the reservoir. So start node is A. And the end node, that's the Robert Burns statue, that's going to be B. And then we need to specify, I think, relationship distance or weight. Yeah, weight property. Relationship weight property is distance. So that's this property here that we're bringing through. So each one of these route relationships has a distance. That's going to be the weight that we're going to consider in this algorithm. Okay, so that's our procedure call. So that's the configuration we're passing in. And then this procedure yields a node ID and a cost. So for the optimal path that it finds, it's going to give us the ID of the node and then the cumulative cost that we've built up. We should be able just to return that. And if we look at, oh yeah, let's not return star, let's return the node ID and the cost. So that gave us kind of a weird output because I was returning both the nodes and tabular data. But here's just the node ID and the cumulative costs measured in meters, I think here. So here's the ID of the first node. So this is the ID for here. So that's the internal Neo4j ID right here, 205. So yep, here's that point. See how far we can follow this path. And then the next one is 4969, which is this one. And says the cost is 15 meters. And yep, 15 meters is the distance on the relationship. And then from here, what's the next one? 4962. Oops, so that's this one. And this distance is 43. So 43 plus 15 is 58. So you can see what's going on there. This is giving us the optimal path to follow. And after 62 steps, we get to where we want to go, 2,800 meters. Okay, let's modify this so we can visualize it in NeoMap. There's a helper function, GDS util, what is it, as node, I think, that we can pass the node ID into that will return the node itself. And then what we want to return is location.latitude as latitude. So NeoMap expects each one of these latitude and longitude values to be returned as latitude and longitude. So we'll just go ahead and do that. And this should just give us a list of latitude and longitude. And now let's copy this, go over to NeoMap, and let's create a new layer. And we'll call this Dijkstra's algorithm. It's going to be advanced. We're going to define it with this cipher query that we copied from Neo4j browser. We want a polyline. Let's change the color to black. And let's see if these paths are different at all. Oh, and they are quite different. That's fun. So, if we zoom in a bit, here's our starting point at the reservoir. And previously we were taking this red path, which is the shortest path cipher function, not taking into account total distance. This time we're going the other way around the reservoir, getting on this path over here. And we end up at the same place. Cool, that's fun. So there are several other algorithms, pathfinding algorithms. The other one here that would be interesting to explore is A star. So A star is similar to Dijkstra in that it considers the paths with the lowest total cost first, as it's doing that depth first traversal. The difference, though, is that rather than just taking the sum of the distance, it also uses a heuristic function. And in this case, that heuristic function is geospatial distance to the destination. So basically, A star is saying, okay, am I getting closer to my destination? And is it also the shortest distance that I've walked thus far. So it sort of factors in this heuristic function, which can be any function really, according to the algorithm, but this implementation in GDS uses geospatial distance. There's, I think, a good Wikipedia diagram that shows kind of the distance, or the difference rather. Yeah, here we go. So here's the same sort of search that we were looking at before. Remember with Dijkstra, we were just sort of expanding kind of aimlessly, but here we're picking the routes that are getting us closer to our destination. So it finds the destination a lot faster. I think I'll skip that one. You can check out, oh, by the way, I should drop a link to the docs for this in the chat. From the chat, wish I code in Cypher like you. Don't make any mistakes, astonishing. Oh no, we make plenty of mistakes. Perhaps we're just having a good day. Cool, so that's the link that I pasted to the A-star implementation in GDS. From there, you can get to, if you look in the sidebar, shortest path for Dijkstra. The difference here with A-star is we have to add the latitude and longitude property keys as well, so that it can figure out the distance to our destination at each iteration. Cool, but we'll leave it at that. What we want to do now is take this Dijkstra implementation and stick this in our GraphQL API, since we know this is going to give us much better results. So what I'm going to do is just copy this part and jump back into our code for our GraphQL API. And here, where it says route to POI, I am just going to replace our naive shortest path example. And let's fix the indentation there. There we go. And let's modify this now so that we'll have Dijkstra GDS instead of Cypher shortest path. So our starting node is this. Remember, in these Cypher directive fields, this is a special keyword that refers to the object that we're currently resolving, which in this case is the point of interest node. And then the end node is going to be other, so the point of interest that we're passing in the POI ID. And then what we return, let's modify this. We're returning this object, but we don't have in scope anymore. Instead, we're calling it node. That's what we're getting back from the call to GDS shortest path. We're using GDS util as node to go from a node ID to the actual node object so that we can read the location.latitude and longitude. Because otherwise here at this point, all we have is that internal ID. So we need to go from that to the actual node in the database. Okay, I think that should do it. So let's see if that works. So I go back to our GraphQL API and It's going to be a little anticlimactic. If I run the same query, now you can see I just get slightly different results. But now we know that this is indeed the shortest path thanks to graph data science and Dijkstra's algorithm. And we looked at this on the map to confirm that, yep, that looks like a good path. Okay, cool. So now we've got that in our GraphQL API. We haven't made any changes to our Gatsby site. I think maybe we'll stop there since the next step is to add the map here and then the detail map for each one of our points of interest, which is going to show the actual routing. So essentially, we're going to want some UI kind of like this, where we're showing like here's where you are, here's where you want to go, and here's the path that you're going to follow to get there. So we'll save that for next time, I think. If you want to learn more about using NeoMap to visualize spatial data and especially paths like this, Estelle wrote a blog post. Let's see, I think I have the link somewhere. Yeah, here we go. Estelle wrote this great blog post. Drop this in the chat. Sort of showing how to do the same sort of visualization of these shortest path functions. She's using cipher projections for the map. So she also shows how to import data from OpenStreetMap using this OSM-INX Python library, which is pretty neat too. But she also shows how to use a cipher projection in the GDS library, which we didn't do. We were using this more configuration-based method for defining the subgraph that we want to use for the algorithm. So if you want to see a different approach there, that's a great blog post. Estelle also recently published a book on graph algorithms and graph data science with Neo4j, which I'll drop the link to that in the chat as well. So this is really cool. It goes into a lot of detail on lots of different graph algorithms in Neo4j, and even beyond that into machine learning, graph embeddings. So definitely check that out. All the code is online as well. So thanks, Estelle, for building NeoMap for the community and also for writing that book. Really cool stuff. Cool. Well, that I think is it for me today. I'll push up the code from today. Really, I guess all we changed in the code is this cipher query in our GraphQL schema. But I'll try to add the documentation and screenshots and stuff too for how to use NeoMap to do some of these visualizations. Cool. Well, thanks everyone for joining today, and hope to see you next week. Remember, we do every Thursday at 2 p.m. Pacific on the Neo4j live stream, talking about using GraphQL and GrandStack with Neo4j. And I will leave you with the link to the full stack GraphQL book excerpt. This is free to download. It's the first 3 chapters of the book that show how to build these backend GraphQL APIs. So focus on the backend rather than the front end. And once we finish this Gatsby project on the stream, we will do a full stack GraphQL Book Club. So stay tuned for that, and don't forget to register for Nodes 2020, the Neo4j Online Developer Expo and Summit online conference coming up on October 20th. Cool. So with that, thanks everyone, and we will see you next time. Cheers.